Good evening, everyone. Sorry for the late, just some problems with the line, so we can start right away. So welcome to this webinar about the compliant mechanisms and how to analyze inside the SIMULIA Structural Simulation Engineer. That is a new app, a new software for SolidWorks customer on the 3D Experience cloud offer of the Dassault system. So basically, let's get started. We are using the webinar, the GoToWebinar platform, so you can input the questions as soon as you have in the panel. So I will have, let's say, the question at the end, so I can answer to you. Also, I will use the survey panel. You will see a blue screen where you can input your answer when I will launch some polls. Also, the webinar is being recorded, so you will receive also a link to review the webinar in some days. Okay, so for starting, I would like to give some credits to two guys, basically the Professor Larry Howell of Brigham Young University of USA for the compliant mechanism work they are doing, and all the files that I've used are available on their website. It's a Creative Commons license, so you can use it. You can also download and use those files. Also, thanks to Veritasium channel, because I've actually be aware of this compliant mechanism because of of this channel. Okay, so let's get started. Let's talk about the classical mechanism. A mechanism is a mechanical device with components, a lot of components, links, and so on, joints, and so on. So basically something that is moving and it's producing a motion, let's say transformations or rotation and so on, translation and so on. But it's basically composed, combined with let's say, some components, some connections. Instead, a compliant mechanism, that is a flexible mechanism, basically it's just one piece, one component that is able to perform the same, let's say, results as a normal, as a classical mechanism, but with just one flexible component. So it's designed very specially with some portion that is flexible and movable or rotated as joints. What are the benefits of compliant mechanisms? There are a lot. Basically, for example, the part count. Of course, this is intuitive. We have a fewer or just one part than a traditional mechanism, so it's better because we can control it better and more precisely. The production process, of course, it's easier because, again, it's just one part or fewer parts than the traditional mechanisms. The price, of course, because basically we can use let's say, we can produce with high numbers, we can use an easier process and so on. So also the price will be affected by the compliant mechanism. The motion is precise because not having bearings or screws and so on, we will not have any gap. So there is small backlash, there is a small wear, and so the motion will be more precise than normal. Also, the performance will be higher because the friction is reduced and there is no need for lubrication. Also, it's very important to understand that it's very easy to miniaturize. The proportions are really important here because for example, in microelectromechanical structure, we can use the compliant mechanism, because it's easily to reduce their size. Also predictability, it's a good thing here because the energy is stored as strain energy. So we have, let's say, very specific, very known value from the beginning. So we know how much energy can be stored, and so it's very high predictable. Of course, with benefit comes also challenges. So which are the challenges of compliant mechanism? Basically, it's difficult to design a complex system to transform it in a compliant mechanism. On the left, on the right, you can see some pseudo-rigid body models to work on, but it's not as easy as you can see. Of course, the behavior is highly nonlinear with large strains and deformations. And the energy storage here is also a problem because maybe not all the energy can be transferred, and so we need to be aware of this effect. The fatigue, it's also a critical issue because we are having, let's say, on flexible portion of the compliant mechanism, a lot of cyclic load, so we have to take into account also the fatigue on these materials. And the motion can be limited. For example, on the bottom you can see the transformation of a rotational joint component, and on the left you can see it's the representation in the compliant mechanism is just a bar that is bending, and so the rotation will be not completed as the normal mechanism, the classical mechanism. So let's say at this point I would like to ask you if you are using physical prototyping in your company. So please answer the poll. Some other seconds to let all of one to vote. Okay, also I will share the poll results. Okay, so this is very in line as usual. So you can see as normal, 50% is using prototypes, but only for main products. Almost 50%. Okay, so another poll, I would like to ask you if you are already using some software in your company to address, let's say, finite elemental analysis or CFD, computational fluid dynamics. Okay, please answer. Some other seconds. Okay. Okay, so let's say most of you are using already SolidWorks products for simulation, and the other are not using or are using some other software. Okay. So let's talk now about the needs, explicitly for the user in such case when you have to analyze compliant mechanism. You need, of course, the ability to understand complex physics, maybe on larger scale. Of course, you need resources for the calculation, for the solving. So maybe in this case, faster and remote computing. Also, since we are talking about high nonlinear stuff, so complex simulation, maybe you need them only when you really need them. So not let's say for necessity every day. And of course, you will need to share these results with your colleagues and all the stakeholders. To do that, we are introducing the 3D experience benefits, so the cloud platform of the system. In this case, with the SIMULIA Structural Simulation Engineer, we are using the SIMULIA technology. We are leveraging Abacus technology with nonlinear and multiphysics capabilities. Also, since it's a cloud platform, we are accessing to more CPUs, explicitly 32 cores for each analysis that you want to run in the cloud. Very important. The subscription model, here we have flexibility because you can buy SSE, you can buy on 3D Experience the apps for 3 months or for a year, and then you can drop it, and when you need again, you will buy again. It's not, let's say, there is anything mandatory here, so a lot of flexibility to use the tool when you need and what you need. The integrated workflow, because it's integrated with SolidWorks. So you will be able to transfer all the necessary information from the model, the boundary condition and so on, from SolidWorks and from SolidWorks simulation, and say transfer to the 3D Experience SIMULIA stuff. Also, since you are already on the cloud, you can share easily all the information within the apps, also on a smartphone or a tablet. Just a matter of inviting another person on the platform to see the results. So here we are really leveraging the SIMULIA stuff, the SIMULIA power, to go to the next level from SolidWorks simulation to structural simulation engineer, based on cloud, so on 3D Experience platform. So we have saw something about it. It's a powerful and robust technology. It's based again on Abacus. It's integrated because we are transferring all the information from SolidWorks, so it's connected also to SolidWorks. And it's cloud-based, so we can solve large models remotely. This is very important when you have some needs to better address all this kind of power and solver capability. You can get to the cloud. From a type of simulation point of view, we can do linear and nonlinear static analysis. We can do frequency and buckling, of course. Also dynamic, linear dynamic analysis, and we have a little bit of multiphysics more in the future. We can resolve thermal and stress situation. Types of problems, for example, gasket sealing or rubber bushing. So all these kind of things that are really complex to analyze in just a linear package. Also metal plasticity with a lot of contacts or bolted assemblies. And to extend this further, things about the SIMULIA technology here, it's really the powerful tool that all the high-end, let's say, analysts are using for realistic simulation, for multiphysics, also cut out for specific industries. We can analyze complex materials as hyperelastic or hyperfoam, or the fracture or the creep model, and so on. And of course, we can easily use the cloud to go to the next level. So let's talk now about the compliant mechanisms. So the case study, the first case study is about these pliers. You saw already the animation in the first slides. I've done the analysis inside the simulation engineer. So here I've used the multiple contacts. I used just one feature that is called general contact. And I don't need to specify any contact set, any contact pairs in the model. So it's very easy to use because you can just input with just one function. You can address all the contacts that will happen in the simulation, and you will see in a moment. I've used an X mesh here, so fast and precise. High precision of simulation, just starting the default dimension. And I've imported the STL file from the Brigham University website. So here I've just used the STL with a lot of facets, a lot of surfaces. So also I was really impressed by the easiness of handling this kind of files. And it was completed at the first run. So let's go to the software. Here you can see I have the model loaded. Here, as you can see, it's an STL with a lot of surfaces. There are no rounds here, no fillet, and I can go to the mesh. So for example, let's try a sweep X mesh. It's just a matter of understanding these kind of things. And you can see in a very quick way, we can address, we can create an X sweep mesh. Also with a refined dimension, I have a nice mesh ready to be analyzed. Okay, so now the next thing will be about the handling of the geometry. Of course, I need to go to the model here, and I need to create a coupling. A coupling is something very important because I can use later and I will show. Here I can just propagate with this simple tool. I can input the degrees of the propagation, and I can easily select more than 100 faces. So very easy to do. And here I have the connector in my tree. So a coupling is something very useful in such situation where you have a lot of faces, a lot of surfaces, you want just to apply one condition that can be a force or displacement and so on. So next thing, now we can define also a coupling here to have also results on the front, let's say, plane of the plier. So the coupling can be used also for results. So let's talk about the boundary condition. This will be just a force on the upper level. Again, I'm using the coupling, and you can see it's very easy to use because the preview is clear. So now I'm applying on the y direction a force, very easily applied. In the other direction, okay. And of course, at this point, I will use the contact. As I said, here I can just activate the tangential and normal contact, and that's it. With this just one function, I have the ability to take up all the contacts. Now I can run it on the cloud with credits. Later on, I will explain better about the credits. And then we can analyze the results. The results are really interesting. I can see, of course, the von Mises stress on the flexible joints of this part. Of course, you can see the not so simple contact that we have here. So multiple contacts handled with just, again, with just general contact. So here I can check my values, if the plastics it's behaving correctly, and so on. This is made in polypropylene. Here I can, of course, I can view the displacement. Again, I can have very nice results, very easily to understand and to navigate. The contact pressure, for example. So here I am seeing the contact pressure that is applied during the steps of the analysis, and so on. So very easy analysis and very nice results. So let's talk about now the second case. It's an actuator. It's a transformation from linear and rotation axis. So you can see here, also in the video with the professor, you can see that is nice picture of an elephant, but in reality it's an actuator from linear to the round part that you can see on the bottom. And you can see down there the analysis that I performed on Simulation Engineer, and we are having the similar results in the software. Here I've used an X-dominant mesh, very powerful and very precise. I will show in a moment. High precision in few minutes. It was just the run was just some minutes, and it was very easy to check the flexible points, the large deformation. So here again we are talking about non-linear analysis, and again it was completed at the first run. So let's go to the software here. Let's go to the model. Again, this is an STL, but easily managed inside SSE. This is the X-dominant mesh with the minimum and maximum size, very easy to do. In some seconds, you can have this mesh. This is very important also because in those points, in those faces that are very near to each other, I need much precision, more precision, so I can easily apply a local mesh, as you can see right now. So I easily selected all those faces, and the mesher has done a great job here to perform an hexahedral mesh dominant. Dominant means that where it needs, you can find, let's say, an X mesh, and where not, a tetrahedral. Also, I added the coupling to the center of those that cylinder, and let's review the feature. Basically, a restraint in the bottom, and the force on the top of this elephant. Very easy setup. So let's review now the results. So again, here you can see the displacement. I can animate the displacement, and you can see that the rotation, it's performed almost perfectly. So from a linear motion on the top, I'm receiving a rotational displacement. Also, I can check the flexible points with the von Mises stress, and it's really powerful to see this kind of analysis. Also, if we are using a coupling, as we introduced earlier, you can see now that I can select the vector components to understand between the linear motion, the rotation plotted in those axes, which is the correlation that I expect to be linear or almost linear, as in this case the angle is very, very near to have a linear correlation to the other transformation. Very interesting. So now let's talk about the third case. It's a flexible gripper. This is for a robotic simulation. Sorry for the Italian, it was a mistake. It's a mixed mesh. So I've used an hex and tetrahedral together in the same environment, the same domain. It's a high complex analysis because we are having a cable that is pulling the top of the gripper, and so it's producing this flexible, this bending of the gripper itself. Of course, as you can see in the images, I've used just a quarter of the model, of the entire model, to reduce the complexity of the simulation. So let's view it in action. So here it's the model. In the middle, you can see there is a cable. It's just a sweep. So this is the mesh, and I can hide this, and I can show the cable mesh. This is an X mesh, very refined, and this is the tetrahedral mesh of the component, of the gripper itself. Here I've applied also, you can see in the tree. Let's position, okay. So a sweep mesh with a very refined control here. and a tetra mesh with a local control, local mesh control here. Why the local control? Because I needed to perform a better mesh on the bottom and all those, let's say, cylindrical holes that are containing the cable. Okay, so very easy to do. Also, from connection point of view, I've used a rigid connection to tie together the end of the cable and the top part of the gripper. Very easy to do. And I've added also coupling, also in this situation, to have it for the boundary condition. So in this case, I've used the coupling for applying boundary condition, in this case, a displacement. So let's review the scenario here. So for example, here we can see the applied translation. It's minus 30 millimeters on the coupling. I've also used the general contact to understand and to assess all the contacts in the simulation, all the self-contact also. The symmetry here, so two planes of symmetry. And so this is the final setup. Okay, let's go to the results. Okay, so let's now switch to the results. This is the stress results in von Mises. Let's again animate the results. And as you can see, now it's loading the results. I can check each step of the analysis and can see the final movement of the cable that is pulled, you can see on the bottom, and the final movement of the gripper that is pulled again on the top. Here is also the displacement, so I can check it also with the mesh superimposed. I can review the results, I can share these results, and so on. Very easily done. Okay, so of course I can plot, I can check each node, I can check each instant. This is very powerful post-processing ability here. Okay, let's go on. Now for the last example, we are referring to this portion where the professor is showing this strange part that, as you can see, and it's printed in titanium. This is a rocket mount usage for say moving a rocket for positioning a satellite. And as you can see, there are two actuators. And those actuators has to be independent one on each other. So I need to have a component that is able to perform independently these two axis rotation. So that's my point that I want to analyze inside SIC. So for this case, I've used a multi-step approach that is a characteristic. It's one of the best features that we have in SSE to analyze all the axis rotation. We will see in a moment how it works. Again, it's a model in STL, and the final results will be also to plot the rotation input versus the rotation output, of course, to check the linear correlation if it's a linear correlation. And the full results I've been able to run in an hour. So let's review here. Let's hide the mesh. So you can see this is an STL, not very smooth. You can see a lot of facets, a lot of surfaces. There is no round, no fillet. And we can easily, again, we can easily mesh it inside SSC. You can see the mesh dimension and so on. also with the second order of tetra, so precise and so on. Also, again, here I've used the coupling feature for the input axis here and for the output. In this case, I'm referring to output because I've used, let's say, a reverse approach to the analysis. But of course, it's a matter as you want to analyze it. So these couplings are also used for boundary condition, but also for plotting the results. Let's talk about the scenario. I've talked about the multi-step approach, and here you can see I've applied 45 degrees of rotation to this coupling, but also I perform, as you can see, there are 5 steps. In the second step, I've applied a -1 scale of factor. So basically, in the first step will be 45 degrees, and the second step will be -45. Also, I perform a third step that is 0 as a scale factor, so it's coming back to the normal position. And I've added also another boundary condition at the fourth step, as you can see here below in the list, for another rotation. And the opposite axis rotation here again with a just -1 scale factor. So here you can see the real power of multi-step approach. Each step is very easy to set up, but in the end I will have all the results of this analysis. So here I have 2 fixed displacement, very easy to do. And now we can see the results, and we are starting from the von Mises stress. Let's again, we can have all the steps that we want, all the multi-steps and so on. So let's review the animation. And here, what I would like to see is how much is independent each movement, each rotation to the other axis. So you can see the stresses. The stresses are, let's say, localized on the component, on the portion that are flexible for just that axis and not the other. And you can see all the steps in one analysis. So very easily to handle inside SSE and very interesting, very nice results. As you can see, also I can plot, I can just probe on the mesh itself the value, for example, for the displacement. Here I want just to control to check the displacement when there is the other axis that is rotating. So very easily done. So let's review also the displacement. Just a moment, it will load. Okay. So again, here I want to understand how much is moving an axis when the other axis is moving. So again, I can see that there is a very good independent movement of those 2 axes. So very nice component design, again, as I told you, by the Brigham Young University. So another results here that I want to show, the fact that I can plot easily the results from the 2 rotation point of view, basically the input and the output. So I can easily check which is one. I want to plot one versus the other to see the linearity of those results. So again, here I can plot how much they are independent and how much they are linear. So very nice simulation of this component. Also, I performed recently another webinar about SSE on those 2 cases, one about plasticity and one about post-buckling. You can review it subscribing to gotostage.com/channel www.pliers.com/Alessandro Bellini. There are for now 2 webinars, and we will be more and more in the future, so you can review it later when you want. Also, you can check our website solidworks.com/SSE, SIMULIA Structural Simulation Engineer, and of course you can write to me. At this point, I'd like to have your feedback. So, which is the level of interest of this webinar? Okay, some other seconds. Okay, perfect. And I'll share it with you. And thank you very much for the feedback. So now I would like to know if you will be, if you would like to be contacted. Of course, for SIMULIA SSE or other simulation products. Some other seconds. Okay, let's close and have a show. Thank you very much for the feedback again. So now I will open to question. Let's see. Of course, you have here my my email address, the YouTube channel. Let's check the question. The first 2 examples appear to be 2D fair problem. Is it necessary to use 3D? No, it's not necessary. Of course, I just used those STL files from the website, but it was very, very fast also to do it in 3D. Why not? Okay, if you are not able to see the webinar completely, or if your connection has some problems, again, the webinar has been recorded and you will receive a link in some days. So another question. I would assume an additional load for the rocket positioning mechanism to include the rocket thrust. Yes, it's a good thing, good question. So basically, yes, it would be nice to also to add another load, and of course you can add another step if you want to add another movement or to check different position and so on. So the multi-step approach in this case, it's helping a lot to address this kind of needs. Also, let me check other questions. There is a question about the cloud. Yes, the product is on the cloud. Again, it's 3D Experience product. So, of course, it's not, let's say, a standalone product. You will need to have the access to 3D Experience Cloud and the access of 3D Experience, the basic access that is called Social Collaboration Services. As we announced, it's free for each one of you has SolidWorks under subscription. So it's a very good point because you can easily get access to 3D Experience and then you can add, for example, SSE. Let's check other question as well. Okay, which are the tools for a hex mesh? Yes, okay. Let's say we have a lot of tools. I've shown only a little portion, but mainly you can use hex sweep mesh, so to sweep a face or a geometry in a linear direction, or also in another direction, in, let's say, non-linear direction. Also, we can use the hex dominant mesh, as we saw, to for other geometry, for more complex geometry. In the hex dominant mesh, you will have brick elements when possible, and the rest will be filled with tetrahedral elements. Okay, so I'm subscribed. Okay, if you are in subscription with SolidWorks, it's not, let's say, automatically added the 3D experience. You have to request to your reseller, and SIMULIA is not inside, let's say, the subscription. Basically, you will have a basic access to the 3D experience platform with the subscription of SolidWorks, and then you can purchase, you can buy SIMULIA application, of course. And you have to ask to your reseller. Okay, I don't see any other questions, so is it possible to get an evaluation? You have to talk again with the reseller because it's specific to region, of course. So again, you have to talk with the reseller. Of course, you can also write to me if there is something, some other information that you need. So it's not a problem. You have my email and so on. Okay, so okay, I think we have done. Again, thank you very much for your participation. Let's meet to the next webinar and have a nice day. Bye bye.